Awesome, thanks. All right, well, I wanted to just give a few brief announcements. We have a few, Ercha Aa is giving us our presentation here on November 5th, and then Carl Landau will give the presentation on December 3rd, right before AGU. We record all of these presentations, as you just heard, and we'll upload them to our YouTube channel. So if you miss it here or would like to view any of the other presentations that we've had as part of the series, please go there. We'll make the title on our seminar page on our website a URL link, so you can go and click from there if you don't want to go directly through the panel, the YouTube directly. And also, if you haven't joined our mailing list, it's growing quite large, but we post updates about the seminar series and also for workshops that come up in the future. So please do so. And then if you know of anyone or are interested in giving a presentation yourself, contact us through our website and we'll make sure to get you on the schedule for 2025. And just with a quick rules of the road before jumping in, if you could make sure to mute yourself so that we don't interrupt the speaker. And if you have questions, feel free to raise your hand or put them in the chat. The speaker's all right with having questions during the talk, so feel free to do that at any point during them, and then when we get to the end, we can have more more questions then. But I am extremely excited to introduce Ercha today. He is a researcher at MIT Haystack Observatory who's done extensive research on both the ionosphere and ionospheric data assimilation methods. And today he's going to be talking to us about a new project where he's done 3D ionosphere imaging with the new TEC-based TIDAS method. So I will stop sharing and let Ercha take it away.
Can you see my screen?
Yes.
Thank you very much. So we know the ionosphere is a highly dynamic region, a very complicated region that undergoes not only considerable climatology changes, but also significant weather disturbances under the influence of solar, geomagnetic, and meteorological influences. So accurately imaging and modeling the ionosphere has always been a challenging task to the space weather community. And today, I'm going to talk about three-dimensional ionospheric imaging with a new TEC-based ionospheric data assimilation system, also known as TIDAS. Here is the outline. So first, I will give a brief introduction of the ionospheric data assimilation. And next, I will talk about TIDAS. TIDAS is a regional data assimilation system. So far, it has 4 versions targeting at different regions over the continental US, over Europe, South America, and East Asia. And next, I will talk about doing space weather analysis by using TIDAS, and followed by the summary. Okay, so first of all, ionospheric data assimilation. We know the ionospheric data assimilation has been proved as a useful technique to specify the ionosphere state, which is implemented by ingesting various data sets into a background model by using certain optimization schemes, such as Kalman filter, variation approach, etc., etc. The ionospheric data assimilation can be classified on the basis of the background models. For example, some data assimilation systems, they use theoretical background models, such as the game model developed by the Utah State University, and the other game developed collectively by the JPL, University of Southern California. And there is a NEMO developed by NRL and APL. They're combining the SEMI3 and IDA40. So the merits of using theoretical background model is that we can provide a physics-based forecast, which is very good. Building upon that, some other data assimilation schemes, they use the coupled ionosphere-thermosphere model, or the coupled ionosphere atmosphere model. For example, we have the TIGCM using DART to do data simulation, and the WACM-X using DART to do data simulation. So the merits of using the coupled model is that the thermosphere state after the data simulation, they can have a relatively slower and long-lasting variation, which may contribute to a longer timescale forecast of the ionosphere through the self-consistent ionosphere-thermosphere coupling mechanism. Of course, we also have empirical background models. They can be used as the background. For example, the AMGEO building on top of the AMI, they can provide a high latitude specification of the electrodynamic. And the Gs, they provide global ionosphere electron density specifications. And there are also some other IRI-based data simulation systems. And we also have IRTAM, ACHIM, Anchor, etc., etc. I mean, there's a lot of great data simulation models. I just don't have time to review each one of them. So please forgive me if I did not mention your excellent models. So with the rapid progress in ionospheric data simulation, we are also facing some needs, like the data needs. We always need new data sets, like ground-based, spaceborne, from above, from below. And we also have the research to operation needs, the R2O needs, that we're thinking of how to improve the nowcasting accuracy, how to improve the forecast ability with better time lead and better uncertainty quantification. But today, I would like to emphasize that we also have a science need, because most current data simulation products, they are building to run on a global scale with comparatively coarse grid size. So they may not always perform the best over the regional ionosphere. So we also have a science needs to resolve regional and localized ionospheric structures with improved spatial temporal resolution. So that's one of the motivations for us to develop TIDAS. So talking about the regional ionospheric data simulation models, we know that there are some operational products that they provide the two-dimensional total electron content results. For example, in NOAA's WAPC, they have a US TEC that provides a quasi real-time TEC nowcast by using the real-time GNSS data. They used to have another version called a North American TEC, but this one was replaced by the GeoDAWG recently. And of course, there are also other TEC products over the South American sectors, over the Europe, over Australia, and over China and adjacent regions. So these operational ionospheric TEC products are great. They can provide quick space weather services. However, we need to know that the TEC is an integrated product. It can reflect the two-dimensional horizontal structures of the ionosphere, but ionosphere is three-dimensional structure. We know that it has very significant altitudinal variations. So we also need to specify the three-dimensional time-evolving electron density variation of the ionosphere. On the other hand, for operational services, it depends on the availability of the quasi real-time data, but not all the data are real-time data. So we also need to emphasize the science needs, that we need to focus by using more data sets to do retrospective studies for time-evolving three-dimension electron density variation studies. So that's another motivation for us to develop TIDAS. So here I'm gonna briefly introduce you to TIDAS data simulation systems. So it is a three-dimensional regional ionosphere imaging data simulation systems. So now it has 4 different versions targeting at different regions. So we have TIDAS over the continental US and TIDAS over Europe, over South America and East Asia. So why did we select these 4 regions to build a data simulation system? The reasons are twofold. So first reason is because of the data coverage. We know that there are relatively ample data coverage over these regions, especially the ground-based GNSS receivers. For example, over the North American region, we have over 2,000 GNSS receivers. So they provide ample data coverage for us to do data simulation. So that's one reason. The second reason is that these regions are characterized by some significant electron density gradient structures that needs to have an in-depth analysis. For example, over the North America and Europe, it's the mid-latitude and the subaurora ionosphere. We can observe the storm-enhanced density plume. For example, here, this panel A shows the electron density distribution at 300 kilometers. This panel B is the ionospheric peak height, F2 region peak height, and F2 region peak density. And this is the total electron content. So we can see this plume-like, channel-like structure with electron density enhancement. So that's the SED plume. We can also saw it in the European regions. So these regions are characterized by subaurora mid-latitude electron density gradient structures like SED plume. Well, in the equatorial and the low-latitude regions over South America, we also have large electron density gradient structures, especially the equatorial ionization anomaly. So we hope to use TIDAS to help analyze the 3D morphology of EIA. And in the East Asian sectors, there are some low latitude and mid latitude electron density structures. For example, for this one, you can see this super plasma density depletion structures that evolved from the equatorial plasma bubbles. So that's why we developed TIDAS for those 4 targeting regions. So let's start from the continental US. So these are the data sets that we use to build TIDAS. First of all, we have the GNSS total electron contents from over 2,000 receivers. We use the line of sight TEC, the slant TEC. So each ray is a line of sight TEC with the color representing its TEC magnitude. And we also use the cosmic radio occultation electron density profiles. So you can see these are the trajectories of the tangent points with the color representing the electron density profiles. And we're also using the JSON TEC. It's the altimeter TEC, a vertical TEC above the ocean surface. And the last but not least, we have the Millstone Hill ISR that provides the altitude resolved electron density distribution, which was also used as our data source. So we ingest these data sources into the background NE-quick model. It is an empirical model which can provide quick calculation of electron density and the total electron content along given 2 points. And we use a ensemble 3D VAR algorithm to do the data simulation. An ensemble-based method is used to calculate the background error covariance, which we know the background error covariance is a critical parameter that directly influences the result of the data simulation. In many prior studies, this background error covariance are usually expressed to be proportional to the ionospheric correlation, which are expressed as a Gaussian-like elliptical function, which is stationary As we can see from here, this panel A and panel B shows the stationary Gaussian-like distribution of the ionospheric correlation. So they are isotropic. But in reality, we know that the ionosphere correlation might not always be isotropic, especially during the space weather event. So many data simulation, they use ensemble method. They run the background model for dozens, scores, or hundreds of times to calculate the ensemble-based error covariance, which is also the way that we did. We run the background model and we calculate the updated error covariance. So like what we show here in panel C and D, so we can saw that it's anisotropic, it's not homogeneous. So there is some difference between the stationary and our background error covariance. It's non-static, it's location dependent. And we use the 3D variation, it's 3D VAR approach to do data simulation. We know that 3D VAR is widely used to do data simulation, which is a statistical optimization method that seeks to minimize a cost function that measures the closeness between background and the measurement. So we use the hybrid ensemble 3D VAR to do data simulation for our regional TIDAS products. Here we show an experiment of the data simulation. That's for the St. Patrick Day storm 2013, March 16 to 18. So these are the histogram before the data simulation, the TEC difference on March 16, 17, and 18. So these are the results after the data simulation. So we can see after data simulation, the distribution is more like unbiased normal distribution with much narrow standard deviation comparing to the before data simulation results. And here we show the electron density distribution at 300 kilometers, which we can see the reconstructed electron density structure showing the SED plume. And there are also some mesoscale structures. Here we show the trajectory of the cosmic. So this is the profile that we show the results before data simulation, after a simulation with cosmic and without cosmic. So we can see after data simulation, the results move closer to the cosmic profile, and the one including the cosmic data performs better than the one without cosmic. I mean, these are quite normal that we put data into the background. We also have a better performance. But here, I would like to emphasize that we would like to use the TIDAS to help us address some scientific questions to show us what scientific new insights that TIDAS can provide us. So the resolution of TIDAS is pretty high, that we provide three-dimensional electron density distribution. The grid size is 1 degree by 1 degree in latitude and longitude, and 20 kilometers in altitude, and 5 minutes, that's the time cadence. So here we show examples of the three-dimensional electron density distribution. You can see this is the horizontal maps at different altitudes. These are the vertical slices. So that's the St. Patrick Day storm in 2013. So we can see these storm-enhanced density plume structures, which we mentioned a lot of times. So SED is a large-scale mid-latitude ionospheric electron density enhancement that are usually observed in local afternoon and evening sectors during the early stages of a geomagnetic storm. SED is usually characterized by a plume-like structure, like what we show here. It's a spatially narrow channel, but with enhanced plasma density that's streaming sunward and poleward. So these three-dimensional structures, now we use TIDAS to do the reconstruction. So we would like to see what new scientific insights can TIDAS provide us? So here we show two examples. The left panel, we show the shaded contour of the F2 region peak density and the peak height, NMF2 and HMF2. So you can see the temporal evolution of the electron density. So we usually describe the SED as a density enhancement, but TIDAS told us SED is not only a density enhancement, but also a layer uplift. You may saw these ridge-like structures. So the height of the SED is higher than its equatorward and poleward counterparts, about 40 to 60 kilometer layer uplift, and a 30 to 50% electron density enhancement. And the right panel show the example of the electron density profiles at Millstone Hill ISR. So there are some data gaps, but we can still see the SED structure here. So these are from the Zenith antenna, and we also have a wide azimuth antenna that scan the wide region. So we can also see this SED plume here. At the bottom panel, show the TIDAS reconstructed electron density profiles, which agrees quite well with the Millstone Hill ISR. So we saw this SED structure here, the SED signature here. If we compare the SED on the storm day to the previous quiet day, we can see that the contribution of SED mainly occur from the topside ionosphere, which means that the electron density above the F2 peak height is increased if we compare this region and this region, but below the F2 peak height, we saw that the electron density is actually reduced. So the TIDAS three-dimensional reconstruction reveals that the primary contribution to electron density enhancement within the SED plume occurs mostly above the F region peak height. Here we show a movie of TIDAS results. We would like to say that it is not only a three-dimensional project, it is actually a four-dimensional product because our time cadence is 5 minutes. So we can see the dynamic evolution of the SED plume, and we can also see some mesoscale structures. So we can see the SED characterized by a layer uplift and electron density enhancement. So the 3D morphology and the dynamic evolution of SED can be reconstructed by using TIDAS with fine scale details. The second version of TIDAS was developed over the European region because this region is also characterized by a large density gradient structures, not only the SED plume, but also the main trough. And there's a dense coverage of ground-based GNSS receivers. Here we show an example of the SED event on February 27, 2023. So we can see the plume structure over the European region. So we would like to emphasize that the SED is not only limited to a certain longitude, it can be a multiple longitude phenomenon, although we usually observe it in the North American sector, but the SED can also be observed over the European region and even Asian sectors. We here show an animation from the TEC polar view. This is the northern hemisphere. So we can clearly see the evolution of the SED plume over the European sectors, then gradually subsided. And after the North American sector rotated to the local afternoon, the SED revived. So it is a multiple longitude phenomenon for SED during this storm event. That's February 27, 2023. And we can also see some SED structures in the southern hemisphere, but due to there are some data gaps, we can saw it a partial SED here in the American longitude sector here, like this. Okay, so If we collectively using the TIDAS over US and TIDAS over Europe, we can analyze the evolution of the multiple longitude ICD plume. Here we show another animation of the TIDAS over European region. So we can see a very dynamic evolution of the ICD plume. They extended from the mainland Europe across Scandinavia, across the British Isles, all the way to the Iceland region. So this is very dynamic. Okay, the next version of TIDAS was developed for equatorial and low latitude regions, because in this region, we also have very large density gradient structure, in particular, the equatorial ionization anomaly. And for South America, we also use ground-based GNSS receivers. So the red dots, they show the location of the GNSS receivers. And we also use the Cosmic 2 because the Cosmic 2 provides a good coverage over the equatorial and the low latitude regions. And this is the JSON3 TEC above the ocean surface. This is the line of sight total electron content. And this is the Cosmic 2 radio occultation electron density profiles. So these are the data sets that we use to do data simulation. And the right panel shows reconstructed three-dimensional electron density distributions. These are the horizontal maps. These are the vertical slices. So we can see the three-dimensional morphology of the EIA structures. So we can clearly see that the EIA was characterized by double peak structures near the after region peak height. But as the altitude increases, this double peak gradually merged into a single peak in the topside ionosphere. So with TIDAS in hand, we can analyze this latitude difference, this longitude dependence, and this altitudinal variation of the three-dimensional morphology of EIA. Here I show another example. So that's a storm event that occurred on November 4th, 2021. So the left panels, we show the electron density after region peak height and peak density and total electron content. That's during the storm day. And the right panels, we show the delta values that we subtract the quiet time reference from the storm values. So we got the delta values. So we can see the variation of the electron density. So in this region, we can see that it was characterized by a positive electron density variation with 30 to 50% increase in the early stages. Then it was gradually replaced by the blue region, which means the density disturbance going from positive to negative. And we can also see there's a layer uplift with HMF2 enhancement during this region. So this positive ionospheric storm, they may be related to the composition effect, which we know that the O/N2 ratio is decreased in the higher latitudes due to atmosphere upwelling, but is increased in the equatorial and the low latitude regions due to atmosphere downwelling. So we saw this increased electron density distribution. Of course, there might also be some contribution from the neutral winds and the electric field. So what we saw that is TIDAS can provide a detailed and altitude resolved information to help us characterize the storm time ionosphere variation in the 3D domain over the equatorial and the low latitude regions. Last but not least, we also have TIDAS over the East Asian sectors. So the data source pretty much the same. This is the ground-based GNSS receivers. The red dots, they are the receiver location. And the green lines, these are the IPP points, ionosphere peers points. So, and we also use the cosmic And here is an example on September 8th, 2017. So we saw these super plasma density depletion structures that occurred in the Asian sector. So they manifest as a parallel dark depletion structures. Here is an animation. Okay, so we can see the dynamic evolution of these super depletion structures. They originated from the low latitude regions, equatorial plasma bubbles, while some of them go very high to the very high latitudes, go all the way to the mid latitude regions, forming these bubble-like super depletion structures. Okay, so that's 4 different versions of TIDAS. Do we have any question here before I move on to the next section? Okay, if no questions, I'm gonna keep moving. So please interrupt me if you have any questions at any time. Okay, next section, I'm gonna talk about space weather analysis by using TIDAS as a tool. So first one is about analyzing 3D ionospheric variations during storms. And the next one is about solar eclipse-induced ionospheric variations. So about the storm time variation, I've already provided several examples. Here I showed some more. So this is the November 20, 2003 geomagnetic storm. So that's the largest storm in solar cycle 23. With the minimum SMH reaching minus 490 nanotesla. So this is the TEC results, which we know there are some data gaps. At the bottom panel show the reanalyzed NMF2 and HMF2 given by TIDAS. So we can see this ridge-like ICD structure with significant layer uplift. So this is the March 17, 2015, the St. Patrick Day storm. We also saw the ICD plume structure here, and that's the TIDAS reanalyzed results. And this is the April 2023. That's the third largest storm in solar cycle 25 to date. And then we also reconstruct the ICD plume structures. So with TIDAS in hand, we can do ICD reconstruction for any given storm. Because of this, we did a very comprehensive, very thorough analysis of all the ICD events during the past 20 years. From 2000 to 2023, we analyzed all the strong geomagnetic storms, and we extracted about 49 events with clear ICD signature over the North American sectors. And we mark the starting time and ending time of the ICD. So for each ICD event, we can do a parameterization. For example, for this St. Patrick Day storm in 2015, that's the reconstructed NMF2 given by TIDAS. If we did a latitudinal cut along this slice, so we could extract these slice, we can see this enhancement. So that's the ICD plume. If we use a Gaussian-like function to do a fitting, so we can parameterize the ICD intensity, that's the height, the ICD location, the central longitude, and the half width of ICD. So previously, when we use TEC to analyze ICD, we usually provide a qualitative analysis. See, it's very strong. But with TIDAS in hand, we can now provide a quantitative analysis of the ICD. And after we did all these ICD reconstruction for these ICD events, we could even do a statistical analysis of the ICD. For example, we show some results here. So that's the distribution of the ICD plume duration. It's about 3 to 10 hours. and that's the drifting speed. We saw that the SED was drifting westward. It's about 50 to 400 meters per second. So we could either do the case analysis by using TIDAS, and we can also do a statistical analysis. So that's the storm studies by using TIDAS. Besides the storms, I would like to talk about solar eclipse, because we know the eclipse is very amazing astronomical phenomenon, but it also provides a unique opportunity for us to analyze the ionospheric variation. It's like a natural experiment. The response of ionosphere to solar eclipse was comprehensively analyzed using total electron content in the past. But with data assimilation, we would like to see what's the difference between each altitude. What are the altitudinal variation of electron density variation? For example, here we show the delta electron density variation at different altitude. So these concentric circles, so they mark the solar obscuration due to the eclipse, because we know that there's a transient cutoff of the solar ionization. So we can saw this passage of the electron density reduction with respect to the passage of the eclipse. And this is the delta TEC and the delta NMF2 variations during the 2017 total eclipse that occurred 7 years ago. And we can see the TIDAS shows us the electron density depletion can exceed 50% around F2 region peak height between 200 to 300 kilometers. The reduction can exceed 50%. So that's very large for the 2017 eclipse. And this is another eclipse event. It occurred 2023, so it's an annular eclipse. So the left panel will show the delta electron density variation at 300 kilometers. So this is the eclipse obscuration, and we can see considerable reduction of the electron density, about 25 to 40% decrease in the mid-latitude regions. And this is the total electron content. This is the delta HMF2 and NMF2. So I have a movie here. So we can see with respect to the passage of the solar obscuration, the ionosphere shows considerable electron density reductions. And if you pay attention to this HMF2 and NMF2, we can see the layer going up and down. For the HMF2 variation, it's very interesting. We can see from here, so that's snapshots from 4 different UT intervals. So after the maximum obscuration, so during the recovery phase, the HMF2 shows a reduction about 20 to 30 kilometer decrease, while the NMF2 also shows a 30% to 50% reduction. So this means that there's a descending layer after the maximum obscuration because the ionosphere was rebuilding from the lower altitudes after the eclipse. So that's why we saw this HMF2 reduction. So this feature was reviewed by TIDAS. And that's the most recent eclipse, the April 2024 total solar eclipse. This time we used SEMI3 as the background to do data assimilation. And we can see this one is the delta NE variation. We can see very clear altitude-dependent response. So the bottom side ionosphere and top side ionosphere, they have different behavior. The bottom side ionosphere, they react pretty fast. There's already some reduction over this region, but the top side ionosphere, they still maintain at pretty high levels. So there's a time delayed response with respect to the altitude increase. And the middle panels, we show the delta NMF2 variations. And we also mark 4 different ionosound stations, the Austin, Boulder, Alpena, and Wallops Island. So that's the electron density profiles during the eclipse day. So these vertical dotted lines and the dashed line, they mark the local eclipse start and maximum and ending. So that's the reference day, which I use the day before and the day after the eclipse as the reference. So we can clearly see that during the eclipse, there's a plasma bite out. And if we do the subtraction, we can see the delta electron density variation, which we can clearly see this altitude-dependent time delay. The bottom side ionosphere reacts pretty fast. There's only 5 to 10 minutes delay in the bottom side, while the top side ionosphere, the time delay is pretty long, even reaching 1 to 2.5 hours after the maximum obscuration. And we can see that the largest depletion occurred around 200 kilometers. It's about 50% reduction. So TIDAS reconstructed these altitude-dependent difference in electron density response. If we pay a close attention to the electron density profiles, these are the delta electron density profiles at a given location. So we can see that in the very beginning, the largest depletion occurred in the bottom side F region, especially in the E region and F1 region. So they reach as large as 40 to 50% decrease. But the top side ionosphere, they still maintain at a pretty high level. Well, after the bottom side ionosphere had already recovered, the top side ionosphere, they started to show large depletion. So we can clearly see this altitude-dependent time delay. In this panel B, we can also see that. So that's the delta NE variation at a different altitude from 100 all the way to 700 kilometers. So these dots, they mark the local minimum electron density after. So we can calculate the time delay between this minimum electron density and the maximum solar obscuration. So we can see in the bottom side, in the E and F1 region, the time delay is very small. It's only 5 to 10 minutes. So it's very immediate response in the bottom side of the ionosphere. But in the top side ionosphere, we can see the time delay gradually increase to about 1 hour to 2.5 hours. So this time delayed variation in the ionosphere was successfully reconstructed by using TIDAS. Okay, here's my summary. So TIDAS is a new TEC-based ionospheric data simulation system for 3D regional ionospheric imaging that utilizes a hybrid ensemble variational approach to do data simulation. TIDAS can provide time-evolving three-dimensional maps of ionospheric electron density distribution. The grid size has a high resolution of 1 degree by 1 degree by 20 kilometers and 5 minutes. So far, TIDAS has 4 versions targeting at different regions over continental US, over Europe, over South America, and East Asian region. So TIDAS can provide a detailed altitude resolved information, helping us to analyze the multi-scale ionospheric structures, such as the SED, the EIA in the 3-dimensional domain. So it can contribute to advance our current understanding of ionospheric morphology and dynamics during space weather events, such as the geomagnetic storms and the solar eclipse. And here is the reference list. That's all my talk. Thank you very much.
Thanks so much for the great talk. We have plenty of time for questions if anyone has any. Feel free now to either raise your hand or unmute and ask your question. All right.
Oh,
Not seeing any. Oh, go
if
for
no
it,
one's
David.
going to ask,
Yeah.
I'll pose a couple then.
Yeah.
So you're using, I guess, a variational approach, which means that you get a sensitivity kernel with that. So you mentioned your resolution is like 1 degree by 1 degree by 20 kilometers and 5 minutes in time or so, but that's not exactly your effective resolution of the assimilation. Um, so I was just wondering, like, given that you can get the sensitivity kernel, which you can use to analytically determine the effective resolution of your assimilation, have you looked at the actual effective resolution that you're getting and how that changes depending on your data distribution or your background model?
Okay, that's a very good question. So I agree with you that the actual resolution is not equal to the grid size. So for some region, we have very dense GNSS data coverage. The actual resolution can be higher than 1 degree by 1 degree. But for some other regions, like over the desert, above the ocean, the actual resolution can be lower than the 1 degree by 1 degree. So we did that for the grid size for 1 by 1, 20 kilometers, but the actual resolution, they can be different as what you have said.
I was more asking, have you actually assessed what the real effective resolution is? Because you should be able to calculate that from your sensitivity kernel
Yeah,
in the variational method.
I have not yet done that, but yeah, I agree with you. I
It'd
should
be
have
really
been able
cool.
to do that. Yeah.
Yeah, it'd be really cool to be able to do that, and then you could also compare to you can see whether or not it has any impact on the scales of the SEDs that you're able to resolve, or if there's like a lower limit on that scale. Um, yeah,
Yeah.
really cool work. Sorry.
Yeah, I agree.
Any other questions for Ercha?
Hi. Yeah, I had a quick, more basic question. So I'm a PhD student, and on your slide, well, there was not a number, but it was the one when you analyzed the storm time ionospheric variations with TIDAS, and then you were quickly mentioning the statistical and quantitative analysis. I would love for you to, if you had 2, 3 minutes, to just go over that again. If you have any extra comments to add, that'll be great. Thank you.
Okay, do you mean this one?
Yes.
Okay, so for this slides, we would like to see that TIDAS can help us to do either case analysis, like the top panel show. We can parameterize the density gradient structures. We can parameterize, quantify its intensity, its central longitude, and its width, so that we know the exact numbers, parameters of the electron density structures. If we combine all those results together, we can have a statistical analysis, like we can calculate the duration of the SED plume. We know that it's about 3 to 10 hours over the North American sectors. And we can also calculate its drifting speed by tracing this variation of the central longitude. We know that the SED plume was drifting westward with an average speed about 50 to 400 meters per second. So I would like to say that with this tool, we can either do case analysis and we can also do statistical analysis.
Okay, thank you so much.
It just blew up the whole thing.
So there's a question in the chat by Anastasia from UCL. She said, impressive talk. Thank you. How long does the model take to run? Is it likely to become operational for space weather prediction, or is it for research only?
For now, it takes about 5 hours to do a daily run. So whether it can be applied to space weather operational services depends on the availability of the real-time data. because what we relied on is a large number of data sets, especially the ground-based receivers. In that case, we can have high resolution results, but for real-time run, we might not always get that large number of data sources. So in that case, the actual resolution could be much lower than the grid size. So for now, we're doing that for retrospective studies. But in the future, if we get ample feed of real-time data, we might be able to turn it into a quasi real-time operational product.
Any other questions from the audience?
I had a quick, really basic one. Piggybacking a little bit off David's previous question, but earlier you mentioned you had seen some kind of mesoscale features in some of your TEC data. I was just wondering kind of reliably what scale sizes you felt comfortable being able to resolve in some of those areas. In terms of a kilometer scale or so forth.
So for the mesoscale structures, in the horizontal plane, I'm comfortable with 1 degree by 1 degree because over these regions, when I do data simulation, I got very dense GNSS receiver coverage. So I think the 1 degree by 1 degree, it's if the mesoscale structure is equal to these kinds of scale, so that would be able to resolved by the data simulation results.
Okay, thanks. I'm more of a magnetosphere person. Do you know roughly what 1 degree at those latitudes corresponds to in terms of spatial scale?
Well, that need to do a mapping
Okay.
from ionosphere
Okay.
to magnetosphere.
Yeah.
So yeah, maybe some experts can do the calculation.
Any
Can I
other
ask a
questions for
question,
Ercha?
Ercha?
Yeah, go right ahead. Sorry.
Yeah. Well, wait, 1 degree is about 100 kilometers, you know, roughly.
Okay.
A little less
Thank you.
as you go toward the mid latitudes, but that, you know, hand waving about. I have one question. Well, first of all, very impressive talk, you know, great work. And I saw when you did the solar eclipse work that you switched the background from, I think you used any quick before and then switched to SAMI 3, if I got that right. And could you say a few words, you know, why you did that? Did you get better results using the physics-based model instead of the more of a climatological model, or what was the reasoning behind that?
Yes. So for SAMI-3, GeoDAWG has a function to mask the solar UV during the eclipse. So that's why the background model, they provide more reasonable variation during the eclipse. By using the NE-Quick, we don't have any mask for solar UV, so the result showed some difference.
Oh, okay. Thank you.
Thanks.
Actually, on that note, can you go to your next slide?
This one?
Yeah. Yeah. So these are from the assimilation, right?
Yes.
So do you have corresponding plots from the background model? Like, so is this trend something that's being extracted from the data, or is this something that's in the background model and you're just kind of pushing a bit? I think it's a little bit towards maybe what Uger's I'm asking about as well. Because if you didn't see it when you did the assimilation any quick, it would mean that your data might not have the ability to resolve that type of structuring. And so you might be heavily reliant on the background here. So it'd be really interesting to see whether or not there's a significant difference between what the background generated and what the assimilation is showing. If there's any innovation there.
Right. So if we're using NE-Quick as the background, we don't see this large altitudinal difference in the background. That's the data created this variation. By using the SAMI 3, because it has the solar UV mask, So there is there's some variation in different altitudes, but not as large as when we have the data to push. So after we ingest the data, it really generated this large difference between the bottom side and top side ionosphere. So I mean, the data really play a big role in creating these different results.
Okay, thank you. Good. Any other questions?
I do actually have one more question that might be basic because I might have missed the 3 or 5 first minutes of this presentation, so I apologize if this was mentioned at the beginning, but what are the possibilities of us adding new datasets to your tool over time, like in the next couple of years or maybe the next few months?
I'm sorry, you mean adding what tool?
To adding new ground-based measurement data sets or satellite measurements to this tool that you're providing the community.
Yeah, we are using the ground-based GNSS receivers. We have four major data sources. So the first one is ground-based TEC. The second one is the cosmic. Depending on the year. So if we have Cosmic 2, we use Cosmic 2. If no, we use Cosmic 1. And we have the JSON TEC above the ocean surface. And the last but not least, if we're doing the TIDAS over the North American, we have the Millstone Hill ISR. So that's the 4 major data source. So do you mean you if there's a possibility to add other data source?
Yes, like for example, in polar regions or other places of interest, which I don't know yet, but I know polar regions can be interesting, for example.
Yes, so the next data source we are considering to add is the Ionosphere data sets, but because some are digisound, they have the automatic scaling results. For that data sets, we need to do a preliminary manual check to make sure that the HMF2 and FOF2, they are reasonable. After that, we may be able to add that into the data simulation tool in the future.
All right, thank you.
Thanks.
Any other questions? This has been a good discussion so far. Okay, I guess we can probably call it there, Adam. Just I guess before we close, I just want to say really thank you, Ercha, for doing the seminar this week and for this month. I'm pretty sure that you're it's like 1 a.m. or 2 a.m. your time now, right?
Thank you very much for providing me with this excellent opportunity. That's my pleasure, my honor.
Yeah, thanks for doing it at such an inconvenient time.
Yeah, if you have any questions, you may check these references.
Perfect. Thank you, Ercha.
Thank you.
Yeah, and thanks everyone for coming. We will upload this to our website just so you can see it again if you wanted to check anything or go back and see any references. And then hopefully we'll see all of you back on December 3rd for Kale's talk, also on ionospheric data assimilation. Great. So thanks everyone. I will end it here.